All right, guys, here we go. This is 2.6. Two questions. As you go through this review, try to keep in mind just starting the question on your own without having to look at any prompts or anything. Really, to me, that's a lot of times the hardest part is just to remember, okay, what should I do in a situation like this? And once you get rolling, it kind of just starts to flow. So use this review as a tool to help you figure out where are the gaps where things that you're not really comfortable starting the question. That's where you should devote extra attention. You can use some of the resources that were listed on the front page, such as redoing classic problems or using the online resources, things like that. But this is just a sampling. It's not really meant to give you all the practice you need if there's something that's uncomfortable for you. So let's just jump into the problem 13 is a gimme question. It's an easy one. This is kind of like 3 points if you see a question like this. It says find the remaining zeros. You're given the degree and some of the zeros. Coefficients, actually, I don't know why it's there. You don't need the coefficients. It's not told to you. Okay, but you got zeros of 3i, 2i minus 3. And you got 5 total, which means you're missing 2. But that's no problem because anytime you have an imaginary root or 0 of the form a plus bi, or complex, I should say, with an imaginary part, we know that the conjugate a minus bi is also a root. So in this case, you have I as a root. That means negative I is also. Because just think about it, that would be like if A was 0, right? If you got A, 0 plus I is the same as I. So 0 minus I, which is negative I. That must be a root as well, right? 0. Okay, and then the other one comes from 2i minus 3 being a 0. They kind of wrote it in a funny way, I think, just to confuse you. But 2i minus 3 is really just negative 3 plus 2i, right? If you rearrange that. So that means the conjugate, negative 3 minus 2i, should also be a 0. Let's do it in a different color. Negative 3 minus 2i. So these are the missing zeros, negative I and negative 3 minus 2i. All right, number 14. 13, that was 13 just now. Number 14 says, for the polynomial below, this polynomial down here, A, determine the number of possible positive and negative zeros using Descartes' rule of signs. That's the pshin. And then determine all possible rational zeros. Typical thing, right? Find the zeros and sketch it. Okay, no problem. Starting with part A. Part A is to find positive and negative zeros using Descartes' rule of signs. That's positive sign changes and negative sign changes. And positive sign changes, looking at the original f of x. Here's positive, positive, positive. Switches to negative. That's the first sign change. And then from negative back to positive. So it's 2 sign changes. That means 2 or subtracted by some even number. So 2 or 0 positive roots. Positive zeros. Yeah. What about negative sign changes? For that, first I got to plug in negative x and see what happens. And quick tip for that, guys, when you're plugging in negative x and you're trying to see what pops out for the polynomial, if it's an even degree, it doesn't matter, right? Negative x to a fourth is going to come back to being positive again. So even degrees just keep their original sign, whatever it was. If it's positive, it stays positive. If it's negative, it stays negative. Odd degrees switch. So if it was positive 30x to the third, now it's going to become negative 30x to the third. 14x squared, that's an even power, it stays. 16x was an opposite because it's an odd power, so it becomes plus 16x. And then 8 is just a constant that stays. Let's count the sign changes this time. Okay, so from positive to negative, that's 1. From negative back to positive, that's 2. And then from there, it just stays the same. So 2 sign changes means 2 or 0 negative zeros. Okay, great. So just now we did part A. We did part B. This was part B here in red. Now part C, find all the zeros. Okay, so to find the zeros, I got a 4th degree. And oh, wait, I'm sorry. I only did part A. Why did I cross out part B? We haven't done part B yet. Part B is determine all rational zeros. Possible rational zeros. Okay, that comes from the last and the first term, right? And the numerator of a rational zero should divide that last term 8. The denominator should divide 9. So starting with the numerator and dividing by 1, right? It's going to give me plus or minus 1. Things that divide 8, plus or minus 2, plus or minus 4, and plus or minus 8. Those are things that divide 8. Okay, I get those as well as the fractions over divisors of 9. So that would be plus or minus 1/3, plus or minus 2/3, plus or minus 4/3, plus or minus 8/3. And then other factors of 9 are 9. So I check plus or minus 1/9, plus or minus 2/9, plus or minus 4/9, and plus or minus 8/9. Okay, so that's part B. Okay, part C says find all zeros now. And to do that, first I'm going to look for 2 using synthetic division and then use the quadratic equation after that. Okay, so let's just use a little intuition here first. I'm going to start with the whole numbers, right? And just looking at, if I plug in 1, this is going to be 9, that's going to be 30, plus 14. It's going to be minus 16 and plus 8. These positive numbers are going to be too much for that negative 16 to overcome and zero out. So I know 1 is not going to work. But let's try negative 1. Negative 1 has a better chance, I think, because at least the 30 and the 16 are going to flip sign. Actually, no, yes. The 16 flipping signs might actually work against us. But let's just try. Okay, so 9 comes down, right? 9 times negative 1 is negative 9, plus 30 is 21. Times negative 1 is negative 21, plus 14 is negative 7. Times negative 1 is positive 7, plus negative 16 is negative 9. Times negative 1 is positive 9, plus 8 is 17. Yeah, okay, so that didn't work. How about let's check negative 2 and positive 2 if that doesn't work. All right, let's try 9. 30, 14, negative 16. I have a feeling like 4 and 8 are going to be too big. But let's just start with the smaller ones, yeah? 1 and negative 1, 2 and negative 2. Okay, 9 comes down. 9 times 2, negative 2 is negative 18, plus 30 is positive 12, times negative 2 is negative 24, plus 14 is negative 10, times negative 2 is positive 20, plus negative 16 is positive 4, times negative 2 is negative 8, plus 8 is 0. Yes, great news, great news. We found our first 0, guys. Great. And that is really good news because I was hoping not to have to delve into those fractions and make things harder and harder for ourselves. So what is the resulting quadratic? This is 9x cubed plus 12x squared minus 10x plus 4. And unfortunately, they don't share any common factors, those numbers. So I can't just divide to reduce. But what I can do is I can start working with this thing. Sorry, this resulting polynomial. And notice the back numbers are 4 now instead of 8. So anything that had 8 in the top, I can eliminate as potential roots. That means this 8 is gone, plus or minus 8. Plus or minus 8/3 is gone. Plus or minus 8/9 is also gone. Okay, what I'm gonna check though is that I'm gonna check if negative 2 is possibly a double root, because that's kind of like somehow where my intuition leads me. It's not always the case, but I'm gonna just check. Since I know it's a root once, maybe it's a root twice. Let's see. I don't have to check negative 1 or positive 1, by the way, because I already checked them with the original polynomial. If it wasn't a root then, if it wasn't a 0 then, it's not going to be a 0 now. Okay, 9 comes down. 9 times negative 2 is negative 18, plus positive 12 is negative 6, times negative 2 is positive 12, plus negative 10 is 2, times negative 2 is negative 4, plus 4 is 0. So perfect. It did, in fact, work out that way. Nice. So that's 9x squared minus 6x plus 2. Okay, at this point, I have a quadratic. So I found 2 of my zeros. In fact, I found 2 of the negative ones. And now I think about it, guys, I should have known. Because once I found 1 negative, I knew there was going to be another negative, right? Because it's got to be 2 or 0. If I find 1, negative 0, it's got to be another one somewhere. And so I got kind of lucky that negative 2 was the same root again. And now from here, it's just pretty basic because I can just go to trusty old quadratic equation. X is equal to negative b plus or minus squared. Negative b is positive 6 plus or minus the square root of b squared, 36, minus 4ac all over 2a. 2 times 9. Okay, inside the square root, let's work that out. Switching colors here. So I've got 6 plus or minus the square root of 4 times 9 is 36 times 2 is 72, but 36 minus 72 is negative 36. So I have negative 36 inside, all over 2 times 9, which is 18. Okay, interesting. This guy, 36 is a perfect square. So I've got basically 6 square root of negative 1, or 6i. So 6 plus or minus 6i up top, divided by 18. Those are all divisible by 3. So that is going to be equal to divisible by 6 actually, right? Divide by 6. 1 plus or minus I over 3. Which is 1 plus I over 3, or 1 minus I over 3. Now, what was the question again? The question I'm working on is find all zeros, right? And I found all the zeros. Let's write them out. So this is part C. Well, part C was actually started up here, where it started the synthetic division. But here's the answer. Negative 2 is a 0. So it's 1 plus I over 3 and 1 minus I over 3. This one is a double 0 or double root. Altogether, if I count that the multiplicity of the negative 2 0, I've got 4 zeros. That's part C. Now, lastly, sketch the graph of the function. Okay, easy. To do that, I'm going to copy that function down here so I have a reference because I'm running out of space. Okay, this is my preferred method here. Now that I have the zeros, right? 14x squared minus 16x plus 8. So I've got 2 imaginary zeros and 1 double 0. So what that looks like on the graph, it means, physically speaking, my graph only crosses the x-axis one time. There's only one real physical 0 that I can point to, which is at negative 2. 1, 2, negative 2, right there. So my graph is going to cross right there, and otherwise it's not going to cross. Okay, what else do I need to know? I need to know the end behavior here. This is, okay, the other thing, this is a double root. So either I approach it and return, or I approach it this way and then return. Right? Those are the 2 possibilities. Now, looking at what I have, the end behavior here reflects 9 to the 4th. So if I plug in a really large number, this is going to be a really large positive number. If I plug in a really large negative number, this is going to be a really large positive number. So either way, you're always positive in this. And so you're going to approach that root and then go back up. Yeah. So hit the root, continue back up. So there's a super rough sketch of our function there. And it's polynomial. So there's no asymptotes to worry about. It's not a rational function. It's no horizontal asymptotes, no vertical asymptotes. Okay, guys, and that's it.